Good morning, everyone. Let's start this last lecture. Actually, this week went like very fast. But I guess you are already a bit tired because of like being here for like 2 weeks. But yeah, one more day left. Okay. Yeah, I will just start because I was noticed that some people were leaving early, so I actually don't know what is the expected number of people for today. Okay, so for today we kind of have two things to do. One is yesterday I started explaining this relation between linear recurrences and matrices, and I think I will kind of continue with that and show you like a cool algorithm that allows you to calculate like high index values in a linear recurrence efficiently, like in n log n log k time in k, where k is the index. It's a clever algorithm, and I think it's beneficial to understand it if you like want to get better in calculating with polynomials and similar representations. Okay, and of course the other part is to like discuss several problems from yesterday. So I guess because I want to do the theory section, and I actually don't want to discuss that many problems together from last day. Rather, I would say if I don't discuss a problem that you are particularly interested in, we can like discuss separately, because yeah, there was one specific thing about yesterday's contest that I did not announce in advance intentionally. So let's have the discussion when we discuss the problem set, and let's start with the theory section, if you don't mind. Okay, so just a small reminder. We kind of argued that if you have like a linear recurrence, so let's say you have some starting values, the first n values are given, and you have a recurrence relationship which allows you to calculate the next term as like a simple linear combination of the previous terms with given coefficients. So it's calculated as somehow like C0, A0, I mean, okay, yeah, in this case, yeah, let's just put it an equals C0, A0 plus C1 times A1 and so on, plus Cn minus 1 times An minus 1. Of course, this is like here the index is a bit overloaded in the sense that, okay, this is the first n terms, this is how you calculate the next term, but actually then you proceed calculating the further terms with the same formula, always using the previous n values. Right? You are familiar with linear recurrences. Okay, so we discussed that there is a matrix form of this. The matrix form was, well, the idea was, of course, to just consider this initial segment of values and map it to, and shift the index by 1. That's gonna be the mapping that we would like to do. And you can already remember that to shift the index, you can use this pattern in the matrix. Always take the element from the next index, and you need to calculate the last element using the recurrence relation. So in the last row we will have the values of C0, C1, C2, and so on, Cn minus 1. This is how the matrix looks like. I think it was something that everything kind of understood. And then there came the few results that I did not prove. One of them is easy to figure out by yourself. If you know what is the characteristic polynomial and how to calculate determinant, then the characteristic polynomial is something like this. It is like x to the power of n minus like Cn minus 1, xn minus 1 minus and so on minus C0 minus C1x minus C0, something like this. You can this is what you can figure out by yourself if you know how to calculate the characteristic polynomial and just expand the determinant. So we skipped this part. Okay, but And yeah, and at this point there was the other thing I mentioned yesterday about the Cayley-Hamilton theorem, which you shouldn't try to prove on your own. It's a relatively deep, difficult theorem in linear algebra, but the result itself is what we're going to rely on in this exploration. And the result is if you substitute the matrix, let's say this is matrix A, if you substitute it into the characteristic polynomial, you get 0. Okay, so this is like a deep result. This is something that I didn't prove, but you can do it for yourself. Okay, and now if you look at this relation, and I think that's where I kind of finished discussing yesterday, if you look at this relation, substitute matrix A, you get 0, or if you rearrange, if you move everything which is negative here to the other side, it is something like this: a to the power of n equals like cn minus 1 a n minus 1 plus cn minus 2 a n minus 2, and so on, c1a plus c0 times, well, for the constant term you always have to consider the identity matrix. It's like the 0th power of a. Right? Okay, so this is the relation that we get. Okay, so both relations are kind of useful on their own way. We want to calculate a to some power of k. Okay, for now just consider this problem. We are interested in the power of the matrix itself. Okay, which can be interpreted as if you consider the x to the power of k value, and if you substitute a, you get a to the power of k. But what I'm claiming is, and I'm not really claiming it, I'm just stating it because it's kind of well known or easy to look up, that for polynomials we have like division with remainder. They work the same way as integers do. It's the same algebraic structure if you have some deeper knowledge in that field. So xk can be written as qx times px plus rx, where px is the characteristic polynomial, so I will keep using p for the characteristic polynomial through the proof. Okay, and this is just the quotient, some polynomial, and this is the remainder, and here the property is that the degree of the remainder is of course lesser than the degree of the divisor p. Okay, so here if we substitute a, and that is why we are interested in this form. Here, if we would substitute a, we would get something like qa times pa plus ra, where pa equals to 0 according to the Cayley-Hamilton theorem. So this is actually just ra. And ra is a polynomial with degree less than n, so it means that we can express the result as a polynomial with degree less than n. More specifically, it is represented by the polynomial which is gained by like dividing xk by px and calculating the remainder. Okay, and so as I discussed yesterday, if you have a concrete example like a to 2000 equals to a plus I, then what we are aiming to do is try to reach a to the power of k, or you could say x to the power of k, by applying an algorithm which is similar to binary exponentiation. So you want to reach higher and higher powers of x with applying binary exponentiation, okay? And we somehow, in each step, want to reduce our result to a polynomial of degree less than n. So for example, if your algorithm, if we know this, and your algorithm at some point reaches like a to the power of like 2048, for example. If you do the binary exponentiation, you will encounter this. Then the idea behind the reduction is this is a to 2000 times a plus I, and you would want to like substitute times a to times a to 48, and you would want to substitute here. So you get a to 49 plus a to 48, something like that. Okay, this is the idea behind what we are going to do. But we are going to do this for the polynomial representation. So we are going to do this with the polynomials, because for the polynomials we already know at least some algorithms. Actually, it is kind of enough to know 2 tricks with polynomials to get to this result. So this gives you a naive idea of what we are going to do. Always like reach a higher power by multiplying or squaring or whatever the algorithm needs, and reduce it to terms that have degree less than r. Okay, you could say that we want to do binary exponentiation for x to the power of k. But modulo the characteristic polynomial. And by modulo I mean we maintain the results such that we only maintain the remainder, saying that the higher degree part is quotient times polynomial, and we just maintain the remainder. Okay, that's what this modulo means. It's not a deep mathematical concept. It just tells you that we always want the remainder, knowing that the rest is a polynomial multiplicand of p. Okay, so applying binary exponentiation is actually useful, because if k is like super large, there is no way to calculate this directly. Because this qx would have like a large degree, sorry. Right? If n is like 2000, this is 10 to the power of 18, then this is almost 10 to the power of 18 degree polynomial. There's no way to directly calculate. Okay, but binary exponentiation is useful because binary exponentiation at most doubles the degrees. So what we are going to do is, during binary exponentiation, we have polynomials of degree at most n. Then after performing a step, we get polynomials with degree at most 2 times n. If we can do the reduction, then we can proceed with this algorithm. Okay, that's the idea. So during binary exponentiation, we need to take into account 2 kinds of operations. Right? We need the squaring and we need the multiplication. So we essentially need to multiply 2 polynomials. And we need to do it at most twice in each step, right? We always need a squaring, and sometimes we need to multiply the current result by the current power of x. So at most 2 multiplications per step. And we have O log k steps. So we should only care about performing 1 particular step. Okay, so can you imagine this? So what I'm doing is the same as binary exponentiation, but with 2 polynomials. I have a polynomial for the result, and I have a polynomial for x to the power of something, but modulo px. Okay, so during the algorithm we are maintaining like the polynomials 1x, x squared, x4, x8, x16, and so on. These are reached by repeated squaring, but we will maintain these polynomials modulo px, So whenever we reach a polynomial, we always want to do this reduction by calculating the polynomial modulo the characteristic polynomial, right? Okay, and we want to maintain the result, which is like a polynomial that sometimes gets multiplied by one of these. So we want to maintain like the answer, which is a polynomial of x, not px. Okay, so we always have one of these and this polynomial, and we perform at most two multiplications. That's how binary exponentiation works. Okay. Understood, right? If there's a question, just say. Okay, so we are going to maintain that. How to do this? Well, I don't really care whether I'm like squaring the current representation of an x power or multiplying two polynomials. I will just interpret it as multiplying two arbitrary polynomials. So we will do this in two steps. I mean each multiplication. First, just multiply two polynomials. Okay, then you get a polynomial. Let's say we get some. So let's call it S, whatever. We get an S polynomial such that the degree is lesser than like 2 times n. Right? What is it's an n degree? Yeah, it's less than 2 times n. Okay, yes. Okay, right? You have two polynomials with degree less than 2 times n. You multiply them. Less than n. You multiply them. This is the result. And this is of course like n log n with FFT. Okay, you already encountered the concept multiple times during the past 2 weeks. This is like now a basic step, let's say. Okay, and now we need to do the reduction. The reduction modulo px. For this we don't have a method yet. And the naive way is like kind of slow. I mean, the naive way is something like take the highest power, reduce it, then take the next highest power, reduce it, but that might take n steps. And each reduction might take like n further steps to maintain the coefficient. So naive reduction is like n squared. You remove the degrees one by one, but you always might do n steps to maintain every coefficient. So sad for us, we cannot do this naively. Okay, so this reduction kind of means that we have this S, and we want to express it in the form of Qx times Px plus Rx. So we kind of have the original problem for Sx with the extra property that the degree of S is actually not that large. Okay, this might have been a bit long explanation, but this is why the binary exponentiation is beneficial. It allows you to only consider small degree polynomials in each step. Okay, so the question is, how can we calculate this? We are interested in the remainder, but actually there's like no easy way to get the remainder directly. Instead, now we don't mind actually computing Qx, because Qx now has like a not too large degree. So here it is feasible to calculate Qx and then just calculate Rx. So that's what we are going to do. We are going to calculate Qx. Okay, so the critical observation is that to determine Qx, you only need to take to determine Qx, you can argue that the following happens. So you take Sx, which is like S2n times x2n plus S2n minus 1 times x2n minus 1, and so on. If you are only interested in Qx, then you could say that, okay, here we have Px, which is like Cn xn plus Cn minus 1 xn minus 1, and so on, plus C0. Okay, and we should calculate the polynomial here until Q is uniquely determined. So what we are going to do is only care about like what values uniquely determine the coefficients of Q, and the rest will be taken care of by the remainder, if that makes sense. Okay, and for this we can actually, for now we can argue what the naive method will do. What the naive method does is, first let's say we want to get this highest degree term, right? You take the highest degree term here, and argue that if you take the highest degree term here, you must get this as the product, because there's no other way to get the highest degree term other than multiplying the highest degree terms, right? So here, this first term, like let's say q n x to the power of n, is uniquely determined by these two. Okay, after that what you will do is take this term, multiply back, you get a polynomial, subtract it from the original, and repeat. Okay, that is how you learned to divide like integers. That is also how you divide polynomials. Okay, so multiply back, subtract. So here we get something from multiplying back, subtract it, and we get a polynomial with one less degree. So like Sn minus 1 prime, plus and so on. And then you like repeat it. To get the highest degree term here, the only way to get it is to multiply the highest degree terms. Yeah, because we already removed this term. We already removed this term, so the only way to get it is to multiply the highest degree terms here. So actually, this and this. This and this will uniquely determine this at this point. And then you repeat. So you will get the value of Qx up until Q0 after considering the first n terms. Right? After considering the first n terms, we get this. Okay, and then just forget about the last n terms. So it turns out that you need to do this until like I mean, it's not necessarily 2 times n, it's actually the highest degree term here, so you could just replace it with k or whatever you want. But the idea is that at this point you uniquely determine q, and yeah, the rest is some trash which we don't care about. Okay, so how to calculate Q based on this observation? Actually, you can notice that the things that we calculated here during the division is like almost the same as what you observed before, like during last week for like multiplying power series or like multiplying polynomials, but from the lower degree up to the higher degree. So notice this. the idea is that we can flip the two polynomials. If you flip S, it means that you take the highest degree term and it will be the lowest degree term from now. So it's like S2n, S2n minus 1 times x plus, and so on. Okay, and you do the same for P, which for then it is like, it's simply Cn plus Cn minus 1x plus, and so on. And after that, based on this multiplication here, it works the same way, working from the highest degree to the lowest degree, as opposite if you work from the lowest degree to the highest degree. So now we can say that if you want to get like S hat or S wave, it is actually Q wave times P wave for the first like n terms. And after that comes this trash part that we actually don't care about. So for the first n terms. Okay, so we just flipped it around. Instead of having to deal with this high index coefficients, we flip the polynomials so that these become the lowest degree terms, and then the multiplication gives you the same result, but the degrees will be reversed in the product as well. Okay, so that's the critical observation, that this multiplication works the same way from both ends of the polynomials. Okay, and after that, we only care about the first n terms here, which means that we don't really care if there is anything after the nth term and what it is. We don't care about that. Okay, so that means we can interpret these polynomials as like power series, like generating functions or something like that, and then just say that, okay, to get Qx, it is Sx over Px, and this is the other like prerequisite beside polynomial multiplication that we need, the fact that if you have this polynomial P wave, then there exists like not necessarily a polynomial, usually there exists a power series such that this holds. Okay, was it covered last week? There's the, if you have a polynomial or more general a power series, the inverse is a power series. Yes. Yeah, I think it was mentioned last week. Franek told me something like that. Okay, so what we are going to do is take the polynomial Sx, calculate this power series, until degree n, and then just multiply to get Q. Because we just need n terms to get Q. Until degree n, and then multiply the two polynomials at that point. Okay, who knows how to get like this inverse power series? Only a few. I don't know, I'm not sure whether it was discussed last week. Last week I was thinking yes. That's what I wanted to build up on this topic a bit. So to compute the inverse of the power series, you could do it naively, saying that, okay, the product of two power series, if you Like the naive way, of course, if this is something that you want to calculate, like zx, then the naive way is to say that one equals like zx times px. And then you just find the coefficients one by one. That is like a slow method, which is not good for us. But you can argue that here you can get the coefficients uniquely determined one by one. The same way as before, actually. Get the constant term that is uniquely determined. If you have the constant, then the first degree term becomes uniquely determined, and so on. Okay, this would be the naive way. Okay, but now since we know that there is a naive way to uniquely determine the inverse power series, this zx, we just need to speed this up. Okay, actually, if I want to be correct, this inverse only exists if the constant term is not 0. But that's not an issue for us because we took the highest degree term from the polynomials, so they are non-zeros. Okay, but it's useful to know that the constant degree term cannot be 0, otherwise there is no inverse. Okay, so the fast way. There are multiple algorithms for this, but the most simple one is like an easy divide and conquer that works as follows. You have like Ex here, and you multiply by P minus X and divide by it, so just expand the fraction. And then the observation is in the numerator, we just get a polynomial, we will deal with this later. And in the denominator, if you calculate this too, this is a new polynomial. This is a new polynomial in terms of x squared. Okay, there are more than one ways to prove this. You can look at the coefficients and you can argue that for even terms, there is a product that takes one term from here, one term from here, and you will get the same product with reversed roles and with negative value because of the odd degree. I mean, to get an odd degree, the odd degree is an even degree times an odd degree. Only that way you can get odd, even plus odd. So if you consider the two ways to get the same term, it turns out that you get it plus once and negative one times. So they cancel out, so you don't get those terms. There's like simple proofs if you know some algebra or like calculus, for example. Don't get into it. Okay, it is. I kind of proved it in an elementary way already. Okay, so this is a fast way because we keep this polynomial for later on, and then we divide the degree by 2 and solve it for 1 over p prime. So this is a simple recurrence that gives you the result. Great. So at this point, we can get Q. So that's pretty good. Now we have Q. We calculate this inverse in like O n log n, and then we do the polynomial multiplication in O n log n. So we finally got Q, and then Q in ordo n log n finally. Okay, after you have Q, you can just compute R, which is S minus Qx times Px. You can now brute force it because this product is also O n log n, and then you just take you just subtract the polynomial that's O n. Okay, so we finally have the remainder. That's great. So now we are able to do the binary exponentiation. Okay, so we are done with this part. Now we have a tool to calculate the high power of x modulo the characteristic polynomial. So we have x to large power of k modulo px. Okay, so now comes the tricky part, because after that we are actually not done yet. If we go back to the original question, how to calculate the linear recurrence itself. Okay, we don't have a tool yet, and this actually tells us that, okay, we expressed xk as some whatever, as some, I don't know, like f0 plus f1x plus and so on plus fn x to the power of n, something like this. Okay, but then we need to substitute, I mean, these are equivalent modulo px. This is the remainder. But finally, we need to substitute a. For which we get equality according to Cayley-Hamilton's theorem, but there we need this linear combination, and we cannot afford to calculate it for the matrices. Right? If we would calculate this for the matrices, that will take a long time, because you need every power of A. So kind of the optimal way is to just calculate the products. Of course, you don't need to do like n square matrix multiplications, because you know in one step you just multiply by a sparse matrix, or in other words, in one step you just shift the index by 1 in the corresponding linear recurrence. So of course, brute forcing this is like n square actually to get all these terms. Okay, so we actually need the terms in the linear recurrence, right? So we actually don't need this. We need ak times the initial vector. So on the other side, we have like a combination of a to l times this vector. Right, so we only need to do this for the sequences. That's why it is. That's why the naive way is actually like n square. Which is still not good enough. So we can speed this up. Or actually, the question is, can we do that? But I kind of gave away already that we can. So how to speed this up? Notice that actually the initial vector is a0, a1, and so on, an minus 1. The last vector is multiplied by an, so that means you take n steps with the recurrence, and in each step you shift the index and add a new term. So the last vector is an times the initial vector, which is simply an plus 1, and so on, a2n minus 1. Right? So actually, and the intermediate vectors have the same terms, but shifting, I mean, dropping one from here, taking one from here. So it is enough to know this last vector. Okay, if you know this last vector, you know every vector on the way. And then we are done. So the question is like how to get this, right? So it is enough to have this, because that way we gain all of the A0, A1, and so on, an plus 1, and so on, A2, and minus 1 terms. So we get every vector here, and that's it. Okay, so okay, yeah, my bad. So the question is like, can we do this? Yeah, sometimes people here like get a bit hasty and say something like, yeah, sure, we can do this, because if somebody studied like generating functions, then you know that for a generating function, calculating all the terms from the initial to some degree can be done in the degree times log degree time with some slightly different algorithms. But we actually don't need any like extra knowledge to tackle this step. Because to be able to do this step, you just have to notice that in the result we are interested in an plus 1, and so on, a2n minus 1. Okay, where each term can be interpreted as performing the linear recurrence. So this is something like C0, A0 plus C, C1, A1, and so on. Okay, for the next term, it can also be interpreted as the result of applying the linear recurrence. So that is actually, we do this with shifted indices. So you notice that it's C0 times A1 plus C1 times A2 plus and so on plus Cn minus 1 An. And you repeat that, so you always do it for the shifted A vector. And so on. Right? Okay, so it seems like, yeah, okay, here we have a sum where the indices are equal. Here the difference of the indices is 1. Here the difference of the indices is 2. That almost reminds us of a convolution, but in a convolution, not the difference, but the sum of the indices is the same. So how to turn this into a convolution? Just flip one of the two vectors. Okay, just flip one of the two vectors, let's say flip or compute in reverse order or whatever, this A0 and so on. A2n minus 1 such that it is A2n minus 1, A2n minus 2, and so on. A0, I mean, these will be the same numbers, I just reversed the indexing. Okay, and with this reversed indexing, we finally find that this is C0 times A. 2n minus 1 plus and so on. This is C1 times C0 times A, 2n minus 2 and so on, and so on. Yep. So now these are coefficients in a convolution. So these are coefficients of a product in a product polynomial. So it turns out to find them, you need to consider the polynomial with these coefficients and the polynomial with the original C coefficients of the linear recurrence and multiply them. So these are convolution or polynom product coefficients. So multiply the corresponding polynomials. Multiply this and this C0 and so on, Cn. So that is once again O n log n, and with that we are finally done with this algorithm. Okay, of course, in the implementation, it's not like 300 lines of codes because many things can be modularized here. So it's actually much faster. With the explanation, it was a bit longer, but it turns out that you just need to use several FFTs, and the trick with calculating the inverse power series. So those are the only two things needed in the end. Okay. Of course, if you have an extensive library of functions that manipulate, power series and polynomials, then some steps can be replaced by some method in those libraries. But this is like a natural way to get the result itself. So, yeah. Okay, questions? No. Okay, so it turns out that the complexity comes from doing FFTs over the binary exponentiation. So in the final complexity, you have a log k factor to this n log m, and that's it. Okay, and it turns out that the method itself does not directly compute one specific term. It's actually useful to calculate n consecutive terms. So the method itself is based on taking the first n terms and then being able to calculate n consecutive terms anywhere in the sequence. Okay, so it's 9:30, so I suggest that we have the break now and then do some problem discussion after the break, if you don't mind. Okay? So let's continue at 10. Yeah, just one remark to the ending of this last section. So yeah, I was like going through the main ideas and expanding them. So I actually missed the minor detail here, which might be important. So when you look at this last convolution, you can notice that yeah, it's a convolution, but it kind of uses the next values that we want to calculate, of course, right? I mean, if you assume that you initially have this slice from the beginning of the sequence, then you calculate the next few terms, but then they start to get used in computing the later terms, right? So it's still like a convolution, but you don't have access to several elements at this point. You could argue that in the initial state, if you just take the convolution between the known terms, you could calculate that part of each sum. Because those only depend on the A entries that you know initially, right? Okay, so after that, well, I was under the impression that there's a trick to do this with like regular Fourier transform. I mean, just multiply two polynomials. I have to think it over, but I might have misjudged it. I might have remembered it poorly because this is also a form of a convolution, but it uses a slightly different kind of an algorithm, which is sometimes called online convolution. It's not like a superpower. Don't get confused. It's for this specific type of issue when you kind of want to like add new coefficient to the top of your polynomial and recalculate the value of the product of two polynomials. So you kind of expand one polynomial as you go. Okay, and there is an online FFT or online convolution algorithm to do that, which is very similar to FFT. It has like an internal tree structure that allows you to do this. So let me just add the remark that you can calculate it with some kind of an online FFT convolution that allows you this specific thing. So you cannot really make a convolution be like a superpower online. This specific issue can be solved when you add like one term from the previous convolution and then recalculate the rest of the slice. You kind of need to like update these parts after getting a new term. Okay, you might want to think about it if you want to. It's actually something that people can figure out, or you can look it up on the internet. I'm not going to explain this particular algorithm. It's just I wanted to point out my mistake because I was under the impression that a regular FFT can be somehow used. I don't see how to do it without this variant, but I might think about it when I have some time. Maybe I'm just not remembering some detail. So. Okay, yeah, so let's discuss the contest and some problems from the contest yesterday. So I did not announce it ahead of the contest, but actually yesterday I intentionally wanted the contest to test your resource management in some form. Now, for one particular problem, it was actually not intentional, but for the types of the problems, I would say they were kind of implementation heavy, and that was completely intentional, because these are the kinds of problems where you might consider swapping the computer multiple times, consider which problem can you implement on paper and then quickly on the computer. So do these kinds of optimizations. So for that, this contest was made for kind of that purpose. The thing that I missed, because I'm just taking a problem package that we have in Hungary or from some other contest and try to implement it or import it into the Codeforces system. So I actually missed that the time limit for this Fibonacci problem was a bit messy. So I'm sorry sorry about that. I had the test data. I had like, I don't know, 10 solutions to it. And yeah, the solutions were running under like 0.6 seconds. So I had no idea that some library implementations, if you plug and play them, then they actually take like much time to execute. So sorry about that, though it's actually still a scenario that you might encounter during the contest. Actually, for this kind of issue, I did not intend to use that problem, though it happened for that problem. I intended to use the Barbarian problem for this. But for the Barbarian problem, it's kind of obvious in some sense that if you read the statement, can you remember the problem? Let's talk about it first then. Barbarian, which was, I think, problem B. Yes. Okay, so the idea was that we have some villages. We have some villages over the real line, given the distances from the shore, so from the 0 actually, and there's a process that, okay, to some village you put the Barbarian, and then it raises all the villages by always going to the closest unvisited village first. Right? And and you had to calculate for each starting village, I don't know how many times it turns directions or something like that. And what was the question?
You had to determine what was the last visit city.
Or the last visit, it's okay, yeah, that also makes sense. I mean, you could ask multiple questions that are answered the same way. You can ask for like the number of turns it takes, the total distance traveled, and those are like all equivalent problems in some sense. Okay, so for this problem, by looking at the statement, if you are like experienced, you might immediately notice that the author of the problem intended the solution to be linear, because of like using like a very large n, and the time limit was like 1 or 1.5 seconds, which is also not too big. So for example, this is a kind of problem where you should probably realize that if you have like an n log n solution, which is a bit easier to come by probably, then you either try to squeeze it or you try to look for a linear solution. I'm actually not sure. I think the teams who got it accepted actually uses the n log n solution, and they had like multiple submissions because they also squeezed it. But yeah, this is also a kind of thing that you might be aware of during the contest. I mean, if something is like over 10 to 6, it's usually intended to be linear or something that you might struggle to squeeze in. Okay, so this problem was for that purpose, kinda. The Fibonacci one was not for that purpose, so sorry for that one, but it was still fitting to the theme of the contest in some sense, so forgive me. Okay, so anyway, for this particular problem, let's consider like how to solve it in linear time. So how to solve this problem. Okay, so as I mentioned, because I also like didn't remember what the final value we want to calculate is, we want to somehow take care of when the Barbarian changes directions. Okay, so we want to somehow simulate or maintain its trajectory. So for example, if it starts from I, okay, for now, let's just suppose that it initially goes to the left. It's like without loss of generality, let's just say that goes left. Okay, and let's notate by, let's say, pi. For I, the pi will be the first village where it changes direction. First village where direction changes. Okay, so yeah, for example, if like this is pi, so if this is pi, then that means that this, oh yeah, that was a mistake. So that means that this distance here, let's say A, is actually greater than, here I made a mistake, so it's greater than this distance B. So it happens if A is like greater than B. Okay, whatever. Okay, something like this. Yep. Okay, so and from here it goes to there, and actually this village here is in this case I+1, right? I mean here from here it starts this direction, so this is the very next I plus first village that is unvisited yet. Okay, so if you think about it, what else does it tell you? Let's think about the villages over like this segment. What happens from I? It goes there. From there, it goes to I+1. Now, for the villages between the two of them, it might visit villages in some order, but at some point, he either gets to I, from where he goes here and go there, or after visiting some villages, it goes to PI, and from PI, you can see that since this is PI-1, the next village in that direction, from PI, even if it like visited some villages here and went there, from there it directly goes to I+1, raising all the villages that were skipped before. Okay, so it means that for any village J between PI and I, at some point it reaches either I or PI and goes to I+1. So it means that for these villages, when reaching I+1, okay, when reaching I+1, then we have that the interval PI and I+1 is cleared, destroyed completely, and everything else is untouched. So everything else untouched.
Sorry, one question.
Yes?
What was PI?
PI is the village where it first changes directions after starting to head this way. PI is well defined in the sense that even if it goes to the very first village, from the very first village, it must change direction and go for the remaining villages.
Okay.
Yes?
Why won't it raise all the villages en route to PI? Like, why would it raise them on the way back? I don't know. That's not that part.
For a given J, or
Yeah, like when it goes.
I mean, inside the interval, almost anything can happen. I mean, inside the interval, there might be a village. I mean, as a starting village. This J is meant for any starting village J. Sorry about that. For I we are already done. Okay. For I, the only observation is that, or the only assumption is that from I it will raise everything until PI, and then it goes to I+1. Sorry, my explanation might have been lacking a bit. So for any J starting village between these, that's what happens. Okay. For any J starting position. Okay, yeah, sorry about that. Okay, so it turns out that if for a given I we know PI, then we know that some things might happen in this interval, but all of these villages will converge to the same state of the whole set of villages at I+1. Okay, under the state I mean the state vector of which villages are raised and which villages are alive. Okay, so it seems like for this interval there might be some prefix of villages visited, but beside that the suffix starting from I+1 is the same for all of them. Okay, any questions to this observation? No? Okay. Okay, so that means we might want to calculate pi for all I. Okay, so we can already like do like a minor improvement. We can, for example, only calculate pi for the villages where the barbarian actually starts going to the left, as we assumed. For the ones where it starts going right, the pi value does not really mean anything. Okay, so we iterate. I goes from 0 to n minus 1. And based on this observation, a clever algorithm to calculate the pi values is to maintain the pi values so far, which actually might be the same for like some subsequent villages. So maintain the values of pi in a simple stack. Stack. It's enough to keep only the different pi values in the stack. You don't need to have multiples. Okay. And then if from a village it goes right, then we can just continue. This is irrelevant. If it goes left, or actually, maybe to make this work, yeah, maybe if it goes right, you can just assume that he itself is pi. Yeah. But anyway, if it starts going left, then you can find. Actually, if it starts going left, you know it's not guaranteed that the next pi will be the answer because the distance to the next village might be like different from compared to the previously processed villages. So actually, what you know is for the next I, the value of pi will be one of those that are already in the stack. It cannot be that a new village will be the pi, because then for some village before the current one, that would be the pi as well. Right? Because of this segment clearing property. So pop from the stack, pop until we find pi. And that's it. You can easily see if that some pi value was popped from the stack, then you won't need it ever later on because of the same observation. Okay, so you just need to understand this geometry over the line. and after that, this simple stack algorithm can help you find the pi values. And also similarly, you can calculate the values to the right-hand side. And actually, after that, you can kind of brute force the solution by like realizing this is some kind of a graph structure where you can do like a traversal with like DPing the answer. So you only need to, so even though for some village you might need to take a lot of steps to calculate the answer, you just save the answers on the way back, and whenever you reach the same part of this tree structure, you immediately know the answer. So you can kind of do it with like DFS traversals plus a simple DP. And that's still linear. So this is linear, and the solution, DFS from each point. with DP, or for this particular one, we kind of store the explicit answer, so you can just call it like memoization if you store like the explicit answer. So with DP, and that's still ON. Okay. Yeah, because you can come up with some n-log solutions with cute observations. For example, it can only change direction at most logarithmic amount of times. So you can kind of try to like brute force the answer by finding the terms. So you can find like n-log square and n-log implementations. You can like improve it with range max queries or something like that. So there are suboptimal solutions. They might need some squeezing because. I mean, I think, I actually don't know, I haven't talked to him, but I think the author intended the linear solution based on like the limits and the method itself. So, yeah. Okay, questions to this? Okay, let's move on. Okay, triangles or triangle counting, I'm not sure what was the title. It was the last problem, so it was L, I think. Okay, so we are given a complete directed graph where initially each edge points towards the vertex with the higher index. Okay, so for example, it's something like this initially. Okay, and we do updates. An update flips an edge. And you have to, for each update, you have to calculate the number of triangles. A triangle is 3 points where the direction is a cycle. So they are directed as a cycle. Count after each update. Okay, well, by construction, you know that initially there are no triangles, but that can change quickly if you start performing updates. So, yeah. Okay, so of course, we kind of want to do what the problem asks us to do, maintain the number of triangles. Of course, the candidates for triangles is like large, and the limits also it doesn't allow us to just take like pairs of points into consideration. That would still be like, you can easily find some solution if you are allowed to compute the, or take the pairs of points into consideration, like store information about that or something. But it seems like we have to do like constant or logarithmic time calculation after each update.
I'm sorry.
Actually, yeah.
What was the number of updates?
The limits were. What were the limits? There was a lot of queries or.
Queries, and n is 10 to the 5, 2 times 10 to the 5.
Okay, so yeah, n is 2 times 10 to 5. Yeah, I was remembering that one of them was large, so the number of questions was 10 to 6. So this is actually kind of the same thing as I explained at the barbarian task. It kind of intends us to do constant time updates, though you might, if you, but I actually don't, here I don't know a solution that uses logarithmic time updates. Being said that, it's the similar situation as in the barbarian task. You either find like the constant time solution per update or have to squeeze it somehow. But here I don't have a logarithmic time update, so yeah. Anyway, this is actually a hint in some form, because if you think that the problem suggests you might be able to do constant time updates, then it kind of means that you just need to take like 1 point into consideration in some form, or just at most the 2 points into consideration which are affected by the update, something like that. So. Well, if you don't have a better idea, then in the worst case, you can think about the possible states of any 3 vertices. I mean, for any three vertices, there are not so many options, right? I mean, you have this, you have this, you have this, you have this, and you have three more where the top edge is flipped. Okay, I'm not going to draw all 8, but it's obvious that you only have 8 configurations for any triangle. Not triangle, any triplet, sorry, any triplet. Because out of these triplets, this is obviously a triangle. And these are the rest 3 states, which are kind of the mirror image of the last 3 I haven't drawn on the blackboard. So we need to come up with an observation. And the observation, well, there are 2 ways to do this. One observation that you can make is, in the cases when there is no triangle, we have one vertex with 2 outer edges, and it's easy to see that. So you have one vertex with 2 outgoing edges. It's easy to see if that's the case, then they cannot form a triangle, obviously. In the triangle you have a cycle. And that kind of means that this is an if and only if description of not having a triangle. Okay, if this happens, you don't have a triangle, and also if you don't have a triangle, then this must happen. So it turns out that 3 points forms a triangle. If and only if exactly one does not form a triangle. Not forms a triangle exactly if exactly one vertex has out degree 2. Okay. So now a bit similarly to the expansion plan, you know, where in the graph we could like draw edges and create connected components, and we needed to enumerate something like a global value. Here we somehow try to globalize this, try to come up with what does it mean in terms of the triangles, or actually in the terms of non-triangles in the whole graph. Because in the whole graph, it's a complete graph. So it means that any 3 points form a triplet connected by 3 edges. So for any 3 points, we have one of these situations, one of the 8 situations, actually. Okay, so that means for any 3 points, I mean for all possible selection of 3 points, we can actually calculate the number of non-triangles. Non-triangles in the graph. How to do that? Consider a point. So consider each vertex individually. Consider a point. It is connected to every point in the graph. Some edges are outgoing, some edges are incoming edges. Okay? We also know that any pair of these endpoints are connected with a directed edge. So what are the non-triangles that we are able to count from the perspective of this vertex?
Every 2 outgoing edges.
If you select 2 outgoing edges from the perspective of this vertex, that gives you one non-triangle, irrespective of how the edge looks like between the endpoints. And all of these triangles will be counted how many times?
Once.
Exactly once, because there is exactly one point having this property in each non-triangle. for every pair of out edges, we can biject them to one non-triangle. We can biject it to exactly one non-triangle. Okay, so what is the number of pairs of out edges? Let's say that xi is the out degree of I. Yes, so you need to choose 2, so it's xi times xi minus 1 divided by 2. Okay, yes? Now, if you want to get the, so these are the non-triangles, so the number of triangles in the whole graph, total triangles. So for the total number of triangles, it is like the number of triplets, right? So it's n over 3, or n choose 3, sorry, minus the sum of these values. For each I. Okay. So, that's great, but of course we cannot calculate this formula in each step. So let's consider the updates. When you do an update, then in terms of like this perspective from one of the vertices, if you flip an edge, then the out degree of these two vertices are affected, but the rest of the out degrees are not affected. So one update manipulates, changes two xi values. So for those two changed xi values, you just update the formula by the difference. So an update affects two xi values. So update two terms in the sum. And that's it. This is a constant time update. So you just start from the initial value, and yeah, the initial value is actually 0 for the triangles, and then do this update. Okay, of course, to do this update, you still need to initialize the number of out edges from each vertex and then do this thing, but it's easy to do at this point. Okay, questions to this? Okay, no questions? Yeah, I mainly wanted to talk about the problems that are nice in some way, not the implementation heavy ones, which are mainly there to test the implementation skills. I might actually not talk that much about this, like this, what is this, the one where you had the railroads. I don't know what was the title, but K, but yeah, I mean the letter was K, but yeah, I don't know what was the name of the problem. It was actually solved in the end by like quite a few teams, so we might not need to discuss it that much. Let's check. I think it was train something. Okay, so yeah, in this problem, the statement was a bit tricky, but you can understand that. Okay, each city will opt to like build one railroad out of it to some other city based on the weights you assign to the edges, because it might opt to like build the lowest cost or highest and lowest, was it highest cost? I don't know if the problem was about corruption or efficiency, but anyway, it either opts to build like the one of the most expensive or most cheap ones. One of them was, sorry? Cheap. Okay, so it was not about corruption. Yeah, it's a Hungarian task, so who knows? So anyway, it was choosing between the two cheapest ones. Okay, so actually, in the problem itself, we are given the railroads that were actually constructed, and we have to find whether it's possible to assign the edge weights such that the construction gives you that graph, right? That was the problem. And yeah, if you think about it a little, you might come up with like an easy symbolization where you say that, okay, this is a city, it has options to build like all the railroads, but it will build one of the railroads, selecting one of two options. So in the end, if it selects to build like this one, then you can try to add the directed edge, saying, okay, this city built a railroad to this city. Okay, and you can consider these edges, and you quickly figure out that this way you obtain a so-called functional graph. Okay, where everyone has one out edge, but might have multiple incoming edges, of course. Okay, it does not matter. These cities can build these two railroads. That's actually not a problem. That is allowed. So this is a functional graph. If you consider these directions. Okay, and then you somehow like need to assign the weights. So you have to be careful about like small edge cases from this point. You kinda need to like not care at all about all the edges that are not mentioned in the graph. So you immediately know that to those you will in the end assign some super high prices and don't mind them. And then you have to be careful about like these things. If you try to think about a construction, you have to think about cases when multiple cities build a railroad towards one city. And you also have to care about like cycles. Okay, right? Yeah, so something that you can try to do is, for example, find the cycle. Okay, over the cycle, assign some weights that guarantees you that the cycle will be created. Yes?
And there is at most one cycle per component, right?
Yes, yes. Mm-hmm. Yeah, for sure, because from any point, if you follow the edges, then you will get a cycle.
Because each point needs to have exactly one edge.
Yeah. Sorry. So the problem itself. Yeah. Okay. Yeah. So the problem itself gives you just the list of the edges without direction, of course. So first you just have to figure out whether the given graph is a functional graph, and yeah, for that you use the property that each component must have at most one cycle. If it has at least two cycles, it cannot be a functional graph, because where two cycles intersect, there is no way to like direct the edges. That's a well-known argument. You can easily prove it by contradiction. So yeah, and after that you can create a direction like this and then assign the edge weights. So for example, you can start from the end. If you already directed the edges, then you can start from the cycle, okay, assign some weights, like in some descending order, let's say, and after that continue to these three components, okay, because it's a cycle with some trees like hanging on it. Okay, so you work your way backwards and assign weights to all of these, and then you just have to make sure that none of the other edges are considered, so you start with some low weights and fill them. Okay, yeah, there were some very easy like pitfalls, like you have to assign different values everywhere and stuff like that. you have to be careful that you don't assign like a negative value. So there are implementation details, but yeah, the main idea was this functional graph idea. Any questions to this? Yeah. Okay. Okay, let's let's do game of strips. Okay, does anyone have an idea how to solve this task? Sorry? Yeah, this was like the extremely difficult task. Actually, if you save some time to think about the interactive task, it can be figured out. For this one, I'm not so sure. It kind of depends like how much you know about game theory. Yes.
Has this been taken in a previous context? And if so, has someone solved it within this time?
Yeah, sorry, what? I didn't understand the question.
Has someone ever solved this in contest time?
I think this is like the second or third time it is used in a contest, and actually there was only one person who figured out the idea but didn't implement it. But some of those guys were super strong, so. So yeah, this is a task that is I mean there's usually a task that you are not intending not to be solved, but it's a kind of a task where you need to have some initial knowledge in game theory, and you need to sacrifice like a lot of time from one person from the team. So it's a bit difficult or like unreasonable to try to solve it. Sometimes sometimes a guy from a team thinks about it a lot and figures an idea, but I guess it's kind of rare. I don't know, I haven't used it in too many contests to have a good sample. Yes?
My team tried but wasn't able to just pre-compute N squared and compress it, send it on the file.
Yeah, that was not the intention here.
I'm pretty sure.
Yeah, I was actually a bit scared because usually the source limit is like, I don't know, like 10 kilobytes or 20 kilobytes at our contests, and on Codeforces it's like, I don't know, 64 or something like that. So actually you might try to compress the values and submit them in some way. Actually, that's also part of why I included the interactive problem. Though for the interactive problem, you can actually solve it on a contest. It's not that one is not impossible for sure. But yeah, for this one, I had in my mind that okay, somebody might be able to squeeze it or cheese it somehow without getting the ideas. But yeah, don't worry too much. I mean, you can always try to upsolve these two problems. I think both of them are difficult. Both of them are super difficult, but also beautiful in their own ways. So it's definitely part of the intention was definitely to introduce you to these two problems and not necessarily to like make you solve both of them on the contest or something. The interactive one was almost solved, I think. There was a code which was kind of using the correct solution, but it was submitted in the last minute, so I guess they just ran out of time. Also, somebody solved it after, I think. Yeah. I think I took a brief look at the code, and I think that's the same idea as I was intending to use. I mean, the problem itself kind of boils down to like try to implement the interactive grader that I implemented and use it on the contestant side. So it's a neat problem. But let's talk about this one because for now it has a bit more instructive value, I would say. So. Yes, in the game of strips, the base idea is that there is a game where you are given like a strip of paper with cells, and you are allowed in each step to divide it, tear it into two parts. tear it into two parts. The condition here was that you are not allowed to tear it into two equal parts. Okay, so in the problem itself, you might choose two strips to play with initially. So the question is, we can have two strips with size at most n. So 3 at least b, that's equal than n. And what are the pairs of strips where the second player wins? So how many A-B pairs guarantee a player to win? Okay, that was the question. So who knows Grundy or Grandi numbers? I'm hoping that mostly all of you, okay? I guess I'm not going to go back to explaining what those are, so for the very few people who haven't, you kind of need to like look up some very basic game theory. It's one of the like the most important core concepts. So yeah, so you might immediately consider Grundy values here, just without explanation. If you want to know how those are computed, the idea is that for each I we will have some gi value. For a strip of length 1 it is 0, representing a losing position. For a strip of length 2 it is also a losing position because you cannot do anything. For a strip of length 3 you can break it down into two parts in one move. And the value is calculated since the game breaks down into two independent games on these two strips. So to calculate it, you take G2, the value corresponding to the the length 2 strip, the game corresponding to the length 1 strip. And if you have a bunch of independent games, the Sprague-Grundy theorem actually states that the corresponding value of the game will be the XOR of these two values. And in this case, this will be 0. Okay? And to get the value of a given position, you consider each state where the game can lead to from the current step in one move, and you take the max, the minimum excluded integer of the sequence. Okay, who knows these concepts that I explained up until now? I guess it's kind of the same people who knew what the Grundy value is in the first place. Okay, so here the only move is this, which leads to Grundy value 0. So the value here is 1. This is the minimum excluded integer. Right? 4, you can only break it to 1 and 3. So this is value 0, this is value 1, the XOR is 1. So the minimum excluded integer is actually 0 because you didn't get a state with the value 0. Okay, and finally for 5, I just wanted to get up until this point. For 5, you actually have two feasible moves, 1 and 4 and 2 and 3. Okay, so 1 and 4, 0, 0, the XOR is 0, and 2 and 3, there the XOR is 1, so the minimum excluded integer is 2. And so this way you can get these values. Okay, this is just for one strip at start, and of course you are still slow to calculate this naively or in a brute force way, because you can see that you actually have like ON moves for n, or O and OI moves when you reach a strip of length I, because you can break it into like any ways except at most one way into two parts. So it's an n-square algorithm to brute force all of these values. Also, I claim that if you would have these values, then you would be able to calculate the answer to the question. value, not I, what is the answer to, what is the answer to the question, yes. Yes, exactly. The frequencies of these Grundy values square, the square sum of the frequencies of the Grundy values. Why is that? It's because if you initially have two strips, then both of them will have some GI value. So the value of the game is the XOR of the A and GB values, and it can only be 0 if the two of them are equal. Okay, the XOR of two numbers is only 0 if the two numbers are equal, because you have to unset every bit. So the answer is, well, if you know how many times some specific G value occurs, then you just need to take pairs of these occurrences and sum them for all Grundy value from 0 to the maximum Grundy value that occurs. Okay, if you actually had the time to brute force it just for experimentation, you know that this maximum is not too large, it's like 230 or something like that. Okay. Okay, so that's the basic outline of what we are facing here. Okay, now my next question is, the statement also mentions it, but it is just a very subtle hint. It's still far from the solution. But the base variant of the game is where you are allowed to break it into equal parts. So you can break it as much as you like. Does anyone know that game specifically? Because that actually appears in quite a few like instructive courses and stuff. Some of you know it. Okay, for that particular game, it's usually used to like demonstrate that in many cases these sequence of GI values have some structural properties, and for that particular game, it becomes periodic after a while, in the sense that there is some slice of values in the beginning, and after 50-something terms, it starts to have a period of, I don't know how many terms, but not that many terms. I think it's only like 7 or 8 values repeating after that. Okay, so for that game, it can be proved by even by a computer algorithm that it becomes periodic very soon, and then it's easy. Okay, so there is like a well-known claim that for any of these composite games, for any of these games where the move consists of breaking down the game into two instances of the same game with smaller sizes. So the claim is, for each of these games, for any of these games, the sequence of Grundy values is periodic. It is actually not directly useful to solve the task. So if you are giving me the looks, I'm not going to say, oh, it's periodic and it's a very simple problem, because that's actually not true. But if you are familiar with this, what I said until now, then only then you kind of have a chance to do something, I guess. So who knew this? That in most cases these games become periodic. Okay, good to know that like multiple students knew it. It's good. Okay, so yeah, for this particular game, actually for this particular game, whether it is periodic or not, and what is the period, has not been discovered yet. So it is an open problem. The periodic part is an open problem, so we cannot use it here. Okay. So if you read any tutorial on solving these problems, of course the advice they always give is, if you have a problem like this, then take the Grundy values, look at the sequence, try to find some structural properties. So that's like always the number one advice. Here we kind of need to do the same. Here we kind of need to do the same, but the observation itself will be like non-trivial. Okay, so I would say if I just say what is the observation for this game, you might say, yeah, that's stupid. But actually, the main idea of the observation can be easily spotted in the basic game, where you are allowed to break it into equal parts. So if you don't have that restriction, for that you very quickly reach periodicity. But actually, I'm just looking at values because I cannot brute force them now. Yeah, so in the original game, where it is allowed to break into equal parts, it turns out that values like 1, 2, 4, 7, and 8 will be part of the period, not in this order, and some of them will be slightly more frequent than the others, but will be part of the period and hence occur infinitely often. They somehow constitute the cycle. Okay, and the rest, for example, like 0, 3, 5, 16. I think these are the only other values that appear. No, of course, the in-between values also appear at least once. Sorry, but anyway, these values occur finite number of times. Yeah, e.g. These are just some values. You can add a few more because you also know that some other values will occur. Okay, so between 8 and 16 there's something going on, but up until 8 there's like a clear distinction between the values in the two sequences. Namely, these have an odd number of bits and these have an even number of bits set. It's actually not that unnatural to look at the bit representation because the XOR is depending on the bits. So you might just as well print the binary representation of every Grandi number. That's even more useful than looking at the number itself. I mean, the number itself just hides the fact that the bits are becoming set or unset during XORing, right? So yeah. Okay, so what is going on in our game? In our game, I mean only one strip because we already deduced that 2 strips is just to make you calculate this value in the end. Okay, we are interested in the G values for 1 strip particularly. The 1 strip variant. Yes?
16 has like 1 strip, right?
Yeah, it's just an example of numbers occurring, but these occur infinitely. And actually, yeah, so this is not a good example. The numbers between 8 and 16, like each appear at most once or twice before reaching the period. So those are not really relevant in terms of statistics. This part is more relevant. So for the low values, it's more useful to look at those. Yeah, but yeah, of course you are right. Okay, so in our game on 1 strip. Well, if you look at the numbers, directly checking like the number of bits set does not really seem to produce a pattern. So this is where you kind of need another critical observation, which is the modification introduced by not allowing equal segments. By not allowing equal segments, you just kind of mess up the last bit of the Grandi value. Because if you will be allowed to break into equal parts, you would fall back to this situation. But sometimes you specifically disallow the last bit to be like set or unset. Disallow it to be unset, actually. And that means that actually the good way to look at the sequence of values in our game is to look at them by discarding the lowest bit, which is a bit chaotic because it exhibits like an alternating kind of property because of like the nature of the game. Sometimes you're allowed to like break into anything. Sometimes you are not allowed to break into equal parts. Yes?
Can you repeat why not allowing this more it messes up the last bit?
So it messes up the last bit because if you were allowed to break it into two equal parts as well, you will get the same game as here, right? If you are not allowed to break it into two parts, then it means that it kind of means that you are removing one value which corresponds to breaking it into equal parts, which corresponds to having a XOR value of 0. So you explicitly remove some 0 XOR value, and that affects your last bit. Okay. So the lowest bit is chaotic or messed up. But if we don't look at the last bit, then it actually seems like we have a similar property. If you just count or if you just look at the values in this, from this perspective, the number of set and unset bits, then it very much looks like that the ones with odd number of bits set are becoming like very frequent, and only a few of them are observed where the number of set bits is actually even. Similar, so it's similar. Odd number of bits set is like common, and even number of bits set is uncommon. Okay, so from this observation we kind of need to, this is like the ground level, the base level of like what to observe about the Grandi values. Now we kind of have to work our way up towards being able to actually calculate something. So because what's going on is something like, okay, we have this kind of like values for smaller strips, and then we somehow take XORs of these, and then we calculate the next G value, and then we repeat. Okay, so we kind of need to think about what is going on when we XOR these kinds of numbers. So it's a property that actually came up over the last like 4 days very frequently, I will say. So XORing kind of means the following. Actually, the very same idea came up in one of the proofs, but okay, maybe it will ring a bell to me as well. I don't know where I was discussing it. So the idea is, I think it was for the XOR convolution, though this problem does not use that actually. So when XORing, you can say that not uncommon, let's use a shorter word like rare. Okay, so when you XOR rare values, if they have even number of bits set, then the XOR will also have even number of bits set, right? I mean, if the set bits are like independent, then of course every bit will be set. So even plus even equals even. If some bits overlap, that reduces the sum of bits by 2. And for every overlap, it gets reduced by 2, so it stays even. So you can directly say it stays rare. Okay, there's another case when this happens, if you think about it, and you quickly figure out that here we are working over like a finite field of length 2, because the other case when this happens is when you have two common values. Common means odd number of bits set. So if you have odd numbers of bits set, if they don't overlap, you get even number of bits set. For every overlap, the sum of bits gets reduced by 2. So that's also a rare occurrence. Okay? And of course, if you do some rare XOR common action, then you always get common, of course, in the converse way as well. Okay, this is actually like a addition over like a finite field of size 2, but so this is the same algebraic structure as what we actually encountered several times during the week. Okay, so you kind of now have to use this to your advantage to squeeze something out to somehow reduce like the complexity. So it turns out that you can actually calculate it if you already have like the brute force just to look at. So you can actually quickly figure out that the number of rare positions or indices. So the number of rare like lengths of strips with GI being rare is like less than, I think it was less than 1,000 and some few hundred. Okay, so this is the number of times when we actually have like a rare value as the Grundy value of the strip. Okay. So the tricky part comes now, which is, of course, okay, we take pairwise XORs of a bunch of numbers, and then we need to determine the max, the lowest excluded, the minimum excluded integer, right? So we somehow need to address that. And yeah, so for some gn value, it is something like this is something like the max of gi, so g n minus I, right? For like I goes from 0 to n over 2 minus 1 if you round up, or n plus 1 over 2 if you wish. No, it was, yeah, sorry, for odd, you go to half minus 1, for even, you go, yeah, for even units, okay, yeah, it's correct, fine. Okay, so what can we do to like speed up this calculation of the new Grundy value? We somehow want to make use of this property, the property that already tells us that the number of like rare positions will be extremely low. We can expect, based on our observation, that the next value will actually be a common value. Some value where we have like an odd number of indices set. So calculating a new value. It is most likely a common type of number, a common value. In some rare cases, I mean at most this number of times, it will turn out to be rare. Okay, so we want to find our candidate. We want to find our candidate for this value. So we want to find like a common value which is as small as possible, which is small and not excluded. So what we are going to do is, since common values are produced by XORing with rare values, so we iterate the common values by maintaining our set of rare indices. We iterate the set of rare indices, that is a small set. For each candidate of those, we immediately knew the size of the remaining part, because n will be broken into like two numbers such that the sum is n. Okay? So we iterate these positions. So let's say pi will be the rare positions so far. Okay? Then we take these values like gpi, XOR g n minus pi. These are common values. And this is the only way to produce common values. So we produce these common values and find the lowest excluded common value. Here you might want to use some tricks to maintain complexity. The trick is to save these indices and also do the max on an array, knowing that the maximum Grundy value that you will ever encounter is like 230. So that allows you to not mess up this part. Okay, find the lowest one. Remember that you only need like a bool array of size 230. Remember that G is at most 230. Okay, so you can quickly find the max, the max among the common values, not the global max, by maintaining a bool array and iterating the array of positions. Okay, so this is like the complexity of the rare positions. This part. Okay, so we have the least common value. Now comes the tricky part. In every case when Gn will be a common value, then all of the lower rare values will somehow get excluded. Okay, and if not, the only case when it does not happen is if all of the lower rare values get produced somehow and gets excluded, then this is our answer, and it happens in the overwhelming majority of the cases, and only just 1,000 times it happens that some rare value lower than this won't get excluded and it will become the G value. Okay, so actually at this point it is enough to try to exclude the rare values. Now to exclude the rare values, note that these were already taken into consideration, because we already iterated the rare indices and just XOR them with any possible pair that they can have for splitting n. So we need to care about the common XOR common types of cases. Okay, so in the next step, iterate the common positions. Iterate the common position and just maintain, using an array and some minimum value pointer, just maintain whether you just need to count. You just need to be able to count the number of rare positions that are still in the game. So you just need to maintain like a counter that tells you whether every rare position has been excluded yet. And check whether every rare has disappeared yet. And if yes, you don't need to continue, so you don't need to iterate every common position. If yes, if not, then in the worst case you have to iterate every common position to get one of the rare positions. Okay, so here the proof is like not complete in the sense that you might think that, okay, but sometimes you might need to look at like a lot of common positions to exclude the remaining rare positions. But it actually does not happen. You can actually speed this part up by like always try to exclude the highest bit of the next rare position. So you can use some tricks to speed it up, but they were actually not required by the problem. And actually this idea that tells you that, okay, so we need O rare for the first phase, and the next step usually ends in O rare steps as well, gives you the idea that this algorithm will work, and actually it passes without optimization. That's indeed the case. Okay, so this happens quickly. So you don't need to. The only case when you need to iterate every common position is when the answer is actually a rare value that is smaller than the least common value. Okay, so this algorithm is like O rare times n complexity, which is actually asymptotically, though it's actually not proved, but it's like it's asymptotically n squared times n. N square root of n times n. My bad. My bad. So it's approximately the square root of n times n, and yeah, this way you can find every g value, and then the answer is as we gave it the start. So yeah, that's a way to solve this problem. Actually, almost the exact same algorithm is used to like reach the record values of this particular game, because it has a record value because the period has not yet been discovered, but actually the values themselves have been computed to up until, I don't know, 10 to 20, I think, something like that. With some optimizations to this algorithm, essentially. So in that sense, this kind of have some instructive value. You can argue that in the original game, actually the same thing happens. Your argument is completely right. It's just that these values disappear completely, relatively quickly. Here they disappear much slower. Actually, the higher you go, the more you get below the square root of n. For this magnitude, it gets to like the square root of n. If you go much higher, it goes even lower. So the square root of n is like not a good approximation. For this particular problem, in the problem set, it's a good approximation, but in general, it's like a stupid approximation. It's not how it works. It kind of goes the other way around. So yeah. Okay. Yes, so with that, time is mostly up, so I think that was the last topic that we explored together. Yeah, I really hope that you enjoyed this week and also the last week, and you liked the topics, or at least like some of the topics that I was bringing up. Of course, as everyone else, I'm bringing topics mostly that I like a bit more than other topics to explore a bit deeper, but during the problem discussions, I think think we also encountered like a lot of different ideas. Yeah, I think the main takeaways were like mentioned during the week, so I'm not going to give a short summary. If you have some time at some point, like during today, I would really appreciate if you give some feedback. Like, I don't know if it was slow, fast, you like the topics, you think that some other topics were lacking, or whatever else. I'm happy to hear any kind of feedback in general. I don't know. Do we have a pizza party tonight or something? Oh, we don't. I don't know if some of you will be at the hotel. I think I will come around to the pool or something. During the week, I kind of had a lot of work to do. I mean, with other stuff I'm involved in, so I didn't socialize that much. But but if some of you want to talk, I will be around the pool, I guess, in the evening. Okay, yeah. Have a safe trip home, and thank you for your attention.